In section 3.3, we discussed homogeneous equations with constant coefficients. And in particular, we talked about how to take such differential equation, create an associated characteristic equation, and then how to identify how to set up the solutions based on the classification of the roots, whether they were real and distinct, real and repeated, or complex. In section 3.4, we're going to build on those topics in the context of an application, namely mechanical vibrations. So I'll be referring back to section 3.3 and some of the topics that we discussed in that section in order to solve these problems in 3.4. So let's talk about what's known as undamped motion. So I have a remark here. Consider an ordinary spring that resists compression and stretching, and suppose that a body of mass M is attached to one end, while the other end is attached to a fixed wall or ceiling. So this spring, again, can be hanging from a ceiling, or it can be being pushed up against a wall, compressed, and then released in the opposite direction. So we're going to say that the equilibrium position is the position when the spring is unstretched, so just left in its natural state. Remark, we denote the distance of the body from the equilibrium position by x, so that x is positive if the string is stretched and it is negative if the spring is compressed. All right, so from physics, you should be familiar with Hooke's law. Hooke's law states that the restorative force F sub s that the spring exerts on the mass is proportional to the distance x that the spring has been stretched or compressed. That is, F sub x is negative kx. Again, we have that constant of proportionality. The positive constant of proportionality k is called the spring constant. All right, so in this case, the system is modeled by the differential equation mx double prime plus kx equals 0. So I just want to make a note right here. This is the dE that's going to model this motion of a spring. I do not want you to memorize this. So whenever you'll need this piece of information, I would provide it on a quiz, exam, or otherwise. So don't memorize. What I want you to focus on in this section is how to solve these problems if given the differential equation that models the motion. All right, so then we have, if we let omega equal the square root of k over m, then we can rewrite the above equation as x double prime plus omega naught squared x equals 0. So all we're doing, and I'll write this in red here, is we can divide both sides, both sides of the equation by m. And what that gives us then is an x double prime plus k over m x equals 0. And so all the book is doing is rewriting the square root of k over m as omega naught. And so to get just k over m, that would be omega naught squared. And so that gets us back down to here. All right, and so it says, since the roots of the associated characteristic equation are complex, then the general solution is of the form here. So the book just kind of states this, but I'd actually like to zero in on this statement so that we really believe it. So let's take this differential equation here, x double prime plus omega naught squared x equals 0, and let's build the associated characteristic equation. So what would that look like? X double prime becomes r squared. And then remember, x just goes to 1. It's the 0th derivative. So we would get plus omega naught squared equals 0. So if we wanted to find the roots here, remember k and m are both positive. So I'll just maybe make a note here. I'm getting maybe too many notes that omega naught is positive since both k and m are positive. K is the constant of proportionality, and so I'll highlight here up above, they specified that that constant is positive, and of course m is a mass, so it doesn't make sense to have negative mass. And so the point here is that if I solve for these roots, I get r squared equals negative omega naught squared, and so r equals plus or minus the square root of negative omega naught squared. We have the square root of negative 1 in there, so that's going to pop out an I, and so we get plus or minus omega naught I. So sure enough, that checks out with what the book is stating right here. And so now we have to think back to section 3.3, which said, how do we handle complex roots of our characteristic equation? So what we do is if we have, I'm going to write over in the other margin, if we have r equals a plus minus bi, then we write out our solution as e to the ax times c1 cosine bx plus c2 sine bx. Now, what do we have here? We have 0 for our real portion, in other words, our a value, and we have omega naught for b. So technically, there's like an e to the 0t here, but remember that's just equal to 1, so we typically don't write it. And then we're seeing our c1 cosine omega naught t and our c2 sine omega naught t, where they're using a and b instead of c1 and c2. All right, so here's how we're getting this equation. This isn't being pulled out of thin air. This is just directly from section 3.3 and analyzing complex conjugate roots. And we find it desirable to combine that cosine and sine function into a single cosine function. So that way we can quickly pick off the amplitude and phase angle. And so to do that, we're going to use the Pythagorean theorem here. C is equal to the square root of a squared plus b squared. And then we also have this alpha value here depending on the signs of a and b. So here again, this is another situation where I don't want you to memorize these equations. If I want you to condense your sine and cosine into a single cosine function, I will provide these equations for you. So just reference them as you're working out the homework problems. And so using those two sets of equations, we can take our original x of t function, which was a cosine omega naught t plus b sine omega naught t, and we can write it in this single cosine function, c cosine omega naught t minus alpha. All right. So that being said, we have a couple of definitions here. Again, things that we can pull off of this equation quickly. The mass oscillates to and fro about its equilibrium position with an amplitude c in meters, a circular frequency omega in radians per second, and phase angle alpha in radians. Such motion is called simple harmonic motion. All right, so we have an idea of the differential equation that models this situation and also some of the pieces of information that we can pull from this. All right, a couple other concepts here before we get into our first example. The period of the motion is the time required for the system to complete one full oscillation. Okay, again, what we're talking about with an oscillation as far as a spring is concerned is, for example, it being compressed and then released back to its equilibrium position, or the opposite, it being stretched and bouncing back and then reaching back to its equilibrium position. So that period is given by 2 pi over omega naught, and that's in seconds. And then its frequency is just the reciprocal of the period, and that's measured in hertz. So that's the number of complete cycles per second. All right, a super important remark here is that mass is assumed to be measured in kilograms in order for this differential equation to hold. We also have force is in newtons, and distance is in meters. So if anything is given to you in any units that are outside of those, you need to convert that first. All right, so we're ready to get into our first example here. This is problem number 4 from the text. A body with mass 250 grams is attached to the end of a spring that is stretched 25 centimeters by a force of 9 newtons. At the time t equals 0, the body is pulled 1 meter to the right, stretching the spring, and set in motion with an initial velocity of 5 meters per second to the left. Part A is to solve the differential equation, find x of t, and they want it specifically in that condensed format of a single cosine function. So before we get started, let's write out all of the information that we have in front of us. So first of all, we have our mass. They give us the mass as 250 grams. Remember up above, I highlighted that mass needs to be measured in kilograms. So we'll go ahead and swap that out for 0.25 kilograms. All right. We also have that this spring is being stretched 25 centimeters. And so since it's stretched, remember that's going to be a positive distance. So that is x equals 25 centimeters. We want the distance to be in meters. So we'll rewrite this as 0.25 meters. And we have a force of 9 newtons. Now, this is important. Remember that your force is always in the opposite direction. So even though we're being stretched, which makes it a positive distance, we write our force in an equal but opposite motion. So negative 9 newtons as opposed to positive 9 newtons. All right, so then it says at a time t equals 0, the body is pulled 1 meter to the right, in other words, stretching the spring. So this is an initial condition on our position function. X of 0 equals a positive 1 meter. And it's set into motion with an initial velocity of 5 meters per second. So I know that my initial velocity is 5 meters per second, and that's to the left, which means it's going to be compressing the spring. So actually, let me indicate that with a negative sign, negative 5 meters per second. And keep in mind how velocity relates to the distance function. Velocity is the first derivative of distance. So in other words, this is an initial condition on the derivative of x. This is all of our given information. So maybe I'll just label this given. All right, now the other piece of information that I will remind you of is the differential equation that models this simple harmonic motion. I would provide this for you on a quiz or an exam. So what we have is mx double prime plus kx equals 0. So I'll maybe also just mention this will be given. All right, so from here, we would like to recover x of t, and then we'll talk about how we're going to condense it to a single cosine function. All right, so I'm going to plug in all of my information. 0.25 x double prime plus kx equals 0. Now, k was not given to us, so we need to go ahead and find that. So remember, I'm going to scroll up here for a moment. Where did k come from? K came from Hooke's law, right? It's related to that force that's being exerted. So what we have is that the spring is being stretched by 25 centimeters by a force of 9 newtons. So our force is going to be 9 newtons, and our distance is going to be that 25 centimeters or 0.25 meters. So let me just set this up here. We have F equals negative kx. And based on our information, our force is negative 9. We have a negative k, and then our distance was a quarter of a meter. And so what we get here is if we solve for k equals positive 36. So let's go ahead and plug that into our differential equation. We had 1/4 x double prime plus 36x equals 0. From here, we can set up our characteristic equation, 1/4 r squared plus 36 equals 0. Let me multiply through by 4. So this gives me r squared plus, let's do this in the margin, 36 times 4, 24, carry the 2, 12, 144. And so I have the sum of two squares. I know that my roots are going to be imaginary, and the square root of 144 is 12. So we get plus or minus 12i. Again, that I coming from the fact that we will be subtracting that 144 over and taking the square root of a negative number. All right, so based on these complex conjugate roots, I can set up my x of t function. All right, we would technically have an e to the 0t, which I won't write. And then we have an a cosine 12t plus b sine 12t. All right, so next we would like to flush out what a and b are equal to using those two initial conditions. So I'll highlight those in green. We had x of 0 equals 1 and v of 0, which is x prime of 0, equals -5. So let's go ahead and impose x of 0 equals 1. That's going to give me a times 1 plus b times 0. So right there, I recover the fact that a equals 1. And now plugging that in, let's go ahead and compute the first derivative. Remember to use the chain rule here and kick out a 12 with each of these functions. So if I plug in 1 for a, the derivative of cosine is negative sine, but it's going to kick a 12 out. So -12 sine of 12t. And then here we still don't know what b is, so I'm going to leave b in there, but we'll kick out a 12b cosine 12t. And now I'm going to impose the second initial condition that the first derivative at 0 is -5. So that gives me a -12 times 0 plus a 12b times 1. And so here I conclude that b is -5/12. All right, so I have now successfully solved for a and b. I most certainly could plug those back in to my solution up here. So I've kind of color coded that. But the reality is they asked me up above, and I'll highlight that also in yellow, they have asked me to write my function x of t in the form c cosine of omega naught t minus alpha. So let's go ahead and write it in that correct order. So let's go ahead and find c. Remember that c is the square root of a squared plus b squared. So that is the square root of 1 plus 25 over 144. So 144 plus 25 is 169. So I get the square root of 169 over 144, which is 13/12. All right, so there's my C value. And then lastly, I need to find alpha. I'm going to note here that A is positive and B is negative. So let's scroll back up to figure out how we're going to identify alpha. All right, A is positive and B is negative, is falling into this bottom category. So I want to take 2 pi plus tangent inverse of B over A. All right, so alpha equals 2 pi plus tangent inverse of B over A. Well, that's just B, right? Because A is 1. And then finally, in conjunction with that alpha, I can write out my condensed form of x of t. That is c, which is 13/12, times cosine of my omega naught t, which was 12t. And then I'm just going to write this as minus alpha, where alpha is stated here in terms of the tangent inverse function. All right, so there is our solution for 4a, and we've written it into the correct format. Part B just says, using your solution from part A, find the amplitude and period of motion of the body. So the amplitude is the easy one to pick off. The amplitude is just the coefficient in front of that condensed cosine function. So the amplitude is c, which is 13 over 12 meters. Again, that just tells how high up and down this function is oscillating. And then we also want to find the period. The period is denoted by capital T. And remember, that's going to be 2 pi over omega naught. So that's 2 pi over 12, which is pi over 6 seconds. All right, so amplitude and period. All right, and so that's problem 4 from the text. Recall that we discussed that this was undamped motion, and I didn't really state what that means, but what we're going to do is we're going to define damped motion next, which will make sense then what undamped motion is. So damped motion, suppose now that the mass is attached to a dash pot, which is like a shock absorber that provides a force directed opposite to the instantaneous direction of motion of the mass. So what I like to think of when I think of a dash pot is if you have a screen door at your home, typically it has like a shock absorber attached to it. So when you open the door and let it go, instead of it slamming shut, it slowly allows the door to shut without slamming. A lot of new cabinet drawers also have a shock absorber so that if you try to just slam the sliding door shut, it'll come so far and then slowly close from there. So I like to think of those things as a dash pot in my head. All right, so definition, we assume that the dash pot is designed so that the force Fr that it exerts is proportional to the velocity v of the mass. So in other words, we can write this as negative CV, where v is velocity, and then of course we can express velocity as the derivative of position. So here again, the negative is coming from the fact that this force is opposite the direction of motion. So we get that negative. The positive constant C is called the damping constant of the dash pot. So here again, we're assuming that C is constant. Definition, if there is no dash pot, then we call the motion of the system undamped. Otherwise, it is called damped. All right, so what is different about damped motion is we're introducing this new summand into the differential equation. So previously we had mx double prime plus kx equals 0, and now we have this new middle term that's involving the first derivative. So here again, we're going to use omega to be the exact same thing, square root of k over m. Again, this is a positive value. And then p is going to be c over 2m. I also noted that that is positive because c is a positive constant, and of course the mass itself is constant. Then we can rewrite the above equation as x double prime plus 2px prime plus omega naught squared x equals 0. So here again, all they're doing is they're dividing everything through by m and rewriting the coefficients. So they say the roots of the associated characteristic equation are as given, negative p plus minus the square root of p squared minus omega naught squared. Let's take a closer look at this, right? Let's confirm. So let's write out our characteristic equation. We have r squared plus 2pr plus omega naught equals 0. Now, I don't really have any information on, whoops, and I forgot my squared on my omega. I don't have any information on the values of p and omega naught. So I'm going to just plug this into the quadratic formula to see what we get out. R equals negative b plus or minus radical b squared, which is going to be a 4p squared, minus 4ac all over 2a. And so I see within that square root that I can factor out a 4. So the square root of 4 is 2. We'll pull that out front. And that leaves a p squared minus omega naught squared inside. And lastly, I can cancel a 2 and top on bottom. And sure enough, that leads me to exactly what we have here, negative p plus or minus the square root of p squared minus omega naught squared. So the real question is, how do we classify these roots? Are they real and distinct? Are they real and repeated? Or are they complex conjugate pairs? And quite frankly, we don't know right now because it totally depends on the values of p and omega. So I kind of zero in here and say, look, we can identify the types of roots that we're working with as long as we understand what's happening under the square root. If that's equal to 0, then our root is repeated, namely it's negative p. If p squared is greater than omega squared, then we're talking about real distinct roots. And if p squared is less than omega squared, then we're talking about complex roots. And so what the book does here is they take the definitions of omega and p and they just flush it out to write out p squared minus omega naught squared in terms of c, k, and m. So here again, the question becomes, what's happening with this numerator? So you have three cases, either c squared minus 4km is positive, which would mean real and distinct roots. Maybe c squared minus 4km equals 0. So those are real and repeated roots. Or maybe c squared minus 4km is negative, in which case we're taking the square root of a negative number, and these are imaginary or complex conjugate pairs. So we would like to analyze each of these three cases and understand how we would move forward with them. So the first case is considered overdamped. This is where c squared is greater than 4km. In other words, we have the real and distinct roots. And the book notes that they happen to be negative in this case. And so then back from section 3.3, we said, well, how do we handle real and distinct roots? We throw those roots inside the exponential function and take a linear combination of those with the C1 and C2. All right, critically damped means that c squared is equal to 4km. In other words, we get that the portion underneath the square root goes to 0, and so we're getting a real repeated root, namely negative p. And so for that, again, we see that root occurring inside the exponential, but we have to tack on this C1 plus C2t because it has multiplicity 2. So that's the repeated root. All right, and finally, we have the underdamped case. Kind of zoom out so we can see them all. And that's where c squared is less than 4km. So here we're going to have a negative value underneath the square root. So we're going to have a complex conjugate pair. And so we're seeing that complex conjugate pair right here. And so what we're going to do is we're going to plug that into our formula here again from 3.3. All three of these were covered in 3.3. The real portion occurs inside the exponential function, and then the imaginary portion right here shows up inside the cosine and sine. So you'll notice what they did here is the original imaginary portion has an omega naught. They're introducing a new variable. They're calling it omega 1. And that's just kind of shortcut here for the square root of omega naught squared minus p squared. All right, and then here again, we can use those same formulas to transform a sum of a sine and a cosine into a single cosine function. I want to just emphasize yet again, I don't want you to memorize these. If I want you to use them on a quiz or an exam, I will provide them. But again, we find it useful to condense the sum of sine and cosine into a single cosine function. And so you'll notice that they have that general solution written right here. From that condensed function, we can pull off omega 1, which is called the circular frequency or the pseudo frequency, and then the pseudo period, which is denoted T1, which is 2 pi over the circular frequency. Finally, we have the time varying amplitude, which is given by this piece here. Time varying because it's dependent on time. As you can see, there's a T in there. All right, So moving on to our last example here, number 16, says for the following problems, assume a mass is attached to both a spring and a dash pot, and the system has the given attributes. Find x of t and determine whether the motion is overdamped, critically damped, or underdamped. If it's underdamped, write the position function as that reduced single cosine function. Also find the undamped position function if the dash pot was removed. There is a lot going on in this problem. So I want to emphasize here, they're assuming, first of all, for you to analyze motion with the dash pot, all right? So that means damped motion. But then they want you to redo the entire equation or the entire differential equation assuming undamped motion. That is, you're just not going to worry about that damping constant C and solve it like we did problem 4 previously. So lots of work to do here in this problem. So let's get started. Let's start with damped motion. And I want to just note here that I provided the whole page, but you're going to need every little bit of that. So just kind of conserve your white space here. All right, so damped motion, just scrolling back up here to page 3. All right, we want to use, let me highlight in green, this differential equation right here. X double prime plus 2px prime plus omega naught squared equals 0. So let's copy that down below. X double prime plus 2px prime plus omega naught squared equals x. Actually, you know what? I take it back. Let's go ahead and let's use the one with MC and K. All right, I'm going to use that one because those are the values that were given. So mx double prime plus cx prime plus kx. Let's use that one. All right, so we have mx double prime plus cx prime plus kx equals 0. All right, this is the differential equation that you'll be given. And then let's go ahead and plug in all of the values that we know. So this is 3x double prime plus 30x prime plus 63x equals 0. And personally, I don't care for all of the threes. Let's just divide everything through by 3. We get x double prime plus 10x prime plus division by 3 gives us 21x equals 0. And then I'll just go ahead and note our initial conditions. X of 0 equals 2 and x prime of 0, which is the velocity, equals 2 as well. All right, now personally, I don't want to memorize all of those formulas that were given up above. If we had them in front of us, we could just plunk in M, C, and K into the formulas. But unless you're planning on memorizing them for the quiz and the exam, I don't really recommend you do it. What instead I recommend you do is running through the characteristic equation and solving using the methods of 3.3. So let's set up our characteristic equation. So that is r squared plus 10r plus 21 equals 0. And so the question becomes, can we factor this by hand? Yeah, this is a nice one. So this is r plus 7 and r plus 3. 7 and 3 add to 10. So we get real distinct roots, -7 and -3. So we know how to set up our solution according to the real and distinct roots. That's going to be a C1 e to the -7t plus C2 e to the -3t. And you'll notice that they had mentioned in the problem statement determine whether the motion is overdamped, critically damped, and underdamped. And what I always say is, I don't give a damp if you know the terms for those. So I'm not particularly concerned whether you know which is which. I want you to be able to solve it. But just so that we're following the directions, let's go ahead and classify what we just found was real and distinct roots. So if we scroll up here, which one did that come in? That was the overdamped case. So right here at this point in time, we can identify this as overdamped. But like I mentioned, I'm not going to ask you to classify these on quizzes and exams. I just want you to be able to solve them. All right, so we have our x of t function. We would like to flush out what C1 and C2 are. So what I know is x of 0 is equal to 2, and that is C1 plus C2, since e to the 0 is 1. Now that's not enough information for me to solve for C1 and C2, so let me use the second initial condition. X prime is going to be a negative 7 C1 e to the negative 7t minus 3c2 e to the negative 3t. All right, so here's our x prime of t, and let's plug in 0. We get 2 out, and that is, whoops, negative 7c1 minus 3c2. All right, so now we just need to solve this system. So I'm going to solve by substitution. If I let C1 be 2 minus C2, then I can plug it into the x prime equation. 2 equals negative 7 times 2 minus C2 minus 3C2. So I have 2 equals a negative 14 plus 7C2 minus 3C2. So 4C2 equals 16. And so what we get here is C2 equals 4. All right, and now let's go ahead and back substitute into our C1. And so I'm going to come back up here. I got 2 minus 4 gives me a negative 2 for C1. So using those two values, I can plug them back into my x of t formula, and I get my final x of t function is a negative 2 e to the negative 7t plus 4 e to the negative 3t. All right, and this right here is x of t. This is my solution to damped motion. Okay, so that's the first half of the problem. Remember, they asked us to solve this assuming damping, but then also to solve it a second time, assuming undamped motion. So the rest of our white space here is for undamped motion. So let's put undamped. And all that means is C is going to be equal to 0. We're not going to have a damping constant. So in other words, we have mx double prime plus kx equals 0. And so I'll plug it in what we have, 3x double prime plus 63x equals 0. Or in other words, x double prime plus 21x equals 0. So here we're going to get our complex conjugate pair when we set up our characteristic equation. So our characteristic equation is r squared plus 21 equals 0, or r squared equals negative 21. And so I get r equals plus or minus I square root 21. And so now we can plug this into our x of t formula. In section 3.3, we learned how to handle complex conjugate roots. And so we're going to get our a cosine square root 21t plus b sine square root 21t. All right, now the question here is, how can we solve for a and b? So again, we're going to use those same initial conditions. We know that x of 0 is 2, but that's going to give me a times 1 plus b times 0. So I get a equals 1/2. And so let me go ahead and plug that in up here. That's going to be a 1/2 cosine square root 21t. We still don't know what b is yet. So now let's go ahead and compute the first derivative. Remember, the chain rule again is going to kick out a root 21 in both of these cases. So we get a negative root 21 over 2 sine root 21t, and then plus a root 21b cosine root 21t. Let's impose that second initial condition that says the first derivative is equal to, or the first derivative at 0 is equal to 2. That gets me a 0 at the sine function and a root 21b for the cosine function. So we conclude that b is equal to root 21 over 2. Oops, excuse me, I wrote the reciprocal. Let's fix that. 2 over root 21. So I'd like to plug that in up here. I'm going to go ahead and do that in red. So I just deleted that b, and I'm going to write in the actual value for b. All right, so right now we have a solution for x of t, but let's scroll back up to the directions here for number 16. It specifically wants us to find the equation as a single cosine function. So we need to use the c and alpha equations to reduce it down. So here's c is equal to the square root of a squared plus b squared. Remember, a was 1/2, so that's going to be 1/4. And then b squared is going to be 4 over 21. Ew, I'm not feeling real good about that. So let's see, what do we get here? Looks like our common denominator is just going to be the product of the two, which is 84. So I get a 21 over 84 plus a 16 over 84. So what's that going to be? A 37 over 84. Okay, let's just make sure everything looks good here. Multiplied by 21 over 21 and 4 over 4. Added those up. Okay, and oh, you know what? I just recognized where my error was. A isn't equal to 1/2, but A is equal to 2. That's where the error is. So let's fix that in red. There it is. There it is. All right. That was an easy enough fix. It doesn't affect anything else, but it did affect my value of C. So let's go ahead and fix it. All right. So we're going to do a 4 here. And if we get a common denominator of 21, that is 84 over 21. And we'll go ahead and just delete this. Sorry about that mistake. Okay. So now we're in business. Let's go ahead and fix this. This is looking a little bit better. So we have 84 plus 4 is 88 over 21. Let's see. Does that simplify? Not particularly, so I think I'll just leave it there. I could pull out a square root of 4 on top, but I'll just leave it as is. And then lastly, we need to find our alpha value. Notice that both A and B are positive values. So when we go up and find alpha, alpha is just going to be tangent inverse of B over A. No need to add on a pi or a 2 pi. So let's go ahead and state here, alpha is tangent inverse of B over A. So I have 2 divided by root 21 divided by 2 again. So that's just going to give me a 1 over root 21. And then in conjunction with that, I have my condensed x of t function, where c is the square root of 88 over 21. And then we have cosine of our omega naught t, which is the square root of 21t, and then minus the alpha that we just stated. So this is our condensed formula here for the undamped motion in problem 16. You know what? That was just so much fun that I want to do it all over again. So let's take a look at problem 18 from the text. Exact same instructions. They want you to analyze damped motion and then do it all over again for undamped motion. So in the last example, when we set up our characteristic equation, we got real distinct roots. Let's see what's going to happen here in 18 with these various mass and damping constant. Okay, so here again, we're going to start with damped motion. We're assuming that damping constant C exists. And we're going to use the formula mx double prime plus cx prime plus kx equals 0. And we'll plug in all of our given information. So 2x double prime plus 12x prime plus 50x equals 0. I like to divide through by that coefficient, so I'm going to call this x double prime plus 6x prime plus 25x equals 0. And then I'll just state my initial conditions. X of 0 equals 0, and the velocity, which is x prime, is equal to -8. All right, so then let's go through the characteristic equation as in section 3.3. That gives me r squared plus 6r plus 25 equals 0. Now, I cannot find factors of 25 that are going to add up to 6, so I'm going to go ahead and plug that into the quadratic formula. R equals -b plus or minus radical b squared minus 4ac, which is going to be 100, all over 2a. So I have -6 plus or minus. I want the square root of -64. So that's going to give me an 8i over 2. So I get -3 plus or minus 4i. So here at this moment, we have identified that we're working with complex conjugate pairs for our roots, and we can identify whether this is overdamped, underdamped, or critically damped. So let's go back up here to our definitions. All right, the complex conjugate pair is considered underdamped. So I'll go ahead and note that, but again, I'm not too concerned if you remember these classifications. Underdamped. All right, so next we would like to set up our solution using the fact that we're working with a complex conjugate pair. So we have e to the real portion of the root t times, and here instead of C1 and C2, the book tends to use A and B in this section, so I'll stick with that notation. A cosine 4t plus B sine 4t. All right, so I have my initial setup. I would now like to find what A and B are equal to. So let's impose 0 here. E to the 0 goes to 1. Cosine of 0 is 1. And sine of 0 is 0. And according to my initial condition, this should equal 0. So what I just got here is A equals 0. And so that's going to simplify my computation. Let's go ahead and simplify that up top. This is an e to the negative 3t times b sine 4t. All right, so now the question is, what is b equal to? In order to find that, I'm going to have to compute the first derivative to use that initial condition. However, I now have a product of two functions in t, so I need to compute that derivative using the product rule. So the derivative of e to the negative 3t is negative 3e to the negative 3t times b sine 4t plus e to the negative 3t times, I'm going to use the chain rule, so that's going to give me a 4b cosine 4t. All right, so now let's evaluate this first derivative at 0. That's going to give me negative 3 times 1 times 0 plus 1 times 4b times 1. And all of this equals negative 8. So when you sift through all of this, we have 4b equals negative 8. So we conclude that b is negative 2. All right. So we have found a and b at this point. And what do we have? What I have is x of t is equal to a negative 2 e to the negative 3t sine of 4t. So here's the really annoying part. Let me scroll way back up to the top of the previous page so that we can look at the instructions for this problem. Okay, it says, find x of t and determine whether the motion is overdamped, critically damped, or underdamped. We just did that. And then it says, if it is underdamped, write the position function as c1 e to the negative pt cosine omega naught, or excuse me, omega 1 t minus alpha 1. They want it in this condensed cosine function. Now it seems silly because the cosine portion went away. Normally we have the sum of a sine and cosine. In this case, because of our initial conditions, a went to 0. But we still want to write it in the correct format. So we need to go through the process of computing C and computing alpha. And so the reason why it's so silly is, remember, we had A equals 0 and we had B equal to negative 2. And so when we find C, C is the square root of A squared plus B squared. But a squared is 0, so it's the square root of negative 2 squared, which is positive 2. So our amplitude is 2. And then how are we going to find our alpha? This is kind of strange. So for alpha, we know that A is 0 and B is negative. So what does that mean? It actually doesn't fall into any of the categories for our alpha equation because those are all based on whether A and B are positive or negative. And none of them are considering when one of them is 0. So instead, what I want you to think of is, think of when x is 0 and y is negative 2. Remember, it was the cosine portion that went to 0 and the sine portion had negative 2. If you think of the unit circle, cosine is always associated with x and sine is associated with y. So think of x as 0 and y as negative 2. Where would that lie on the coordinate axes or on the unit circle? You would be on the lower y-axis. So that corresponds to an angle of 3 pi halves, right? You've gone through 3 full quadrants and you're pointing in the downward y-axis. So given that piece of information, we can now find x of t as the book wants us to. Our C value was a positive 2. You're going to rewrite your e to the negative 3t. And instead of a sine function, you now have cosine of 4t minus your alpha, which we actually found directly as 3 pi halves, rather than writing it in terms of a tangent inverse. Hoo-wee. All right, that was just the solution for damped motion. Let's finish this off with undamped motion. All right, so now we're moving on to undamped. Here again, we're using mx double prime plus kx equals 0, and then plugging in the information that we know. So we had m equals 2, and we had k equals 50. So if we divide through by 2, x double prime plus 25x equals 0, with the initial conditions x of 0 equals 0 and x prime of 0 equals -8. All right, so let's run through the motions. The characteristic equation would be r squared plus 25 equals 0. Those are going to give us complex roots plus or minus 5i. And so we get x of t equals a cosine 5t plus b sine 5t. And let's go ahead and impose those initial conditions. X of 0 equals a times 1 plus b times 0, and that equals 0. So here we're going to conclude that a equals 0. And so I'll just actually plug that in up top. Our function now reduces to b sine of 5t. So let's use the first derivative here is going to be a 5a, nope, not an a, of 5b cosine 5t. And if I plug in 0, that gives me 5b times 1 equals -8. So b is -8 over 5. All right, so we have now solved for a and b. Kind of a similar situation here. C is the square root of a squared plus b squared. That just makes c into the positive b value, so 8/5. And then here again, we're going to get alpha equals 3 pi halves because we have 0 for a and a negative b. We're down on the negative y-axis. And so our condensed x of t function is going to be 8/5 cosine of, we keep that same 5t inside, but we're shifting it 3 pi halves. So here is our solution for undamped motion. All right, so this concludes our section here, 3.4 over mechanical vibrations. And up next, section 3.5, it's a long one. I'm going to split it into 2 separate videos. We're going to learn how to find the solutions for non-homogeneous equations, and we'll talk about how that relates to 3.3 with the homogeneous equations.